Hello everyone and welcome back. In this video we're going to talk about conditional probability, and then we'll use this to define independent events. When we're looking for a probability of an event that comes from a conditional distribution, then we write P bracket B vertical line A and say the probability of B given A. And this is called a conditional probability, and it will ask for the probability of B given that A has already occurred. And to find this conditional probability, we will restrict our attention to the outcomes in A, and then we find what fraction of those outcomes B have also occurred. So mathematically, the probability of B given A is the probability of A and B divided by the probability of A. So let's take a look at an example. So given that the result of rolling a fair six-sided die is an even number, then what is the probability that the die roll is 2? So intuitively, if we're given that the outcome of a die roll is one of 3 even numbers, then the probability that the outcome is 2 would be 1 out of 3. But now let's also practice calculating this conditional probability by using our formula. So let's first define our events A and B. So here the event A is the given event, and we are given that the die roll is an even number, so it can be either 2, 4, or 6. And the event B is the number 2. And so we're looking for the probability of B given A, which is the probability of A and B divided by the probability of A. So let's take a look at the probability of A and B. So we want to look for the intersection of these two events. So what is the intersection of the events A and B? Well, we want to look for the events which are common between both of them. And we see that there is only one event or outcome which is common, which is the number 2. So the intersection of A and B is just the result of 2. And so the probability of A and B is the probability of rolling a 2, which is 1 out of 6. Now we also need to determine the probability of A. So the probability of rolling an even number, well, there's 3 outcomes out of a total of 6, which can be reduced to 1 over 2. And so now we can calculate the probability of B given A. So the probability of A and B divided by the probability of A. So we can calculate this. This will give us 1 out of 6 divided by 1 out of 2. And rather than working with 2 fractions, let's rewrite it so that we only have 1 fraction. We can multiply by the reciprocal of the denominator. So we have 1 out of 6 times the reciprocal of 1/2, which is 2 over 1. So this will simplify to 2 over 6, or 1/3. So now let's take a look at an example of finding probabilities by using a contingency table. So this table shows the counts of Canadians visiting Stonehenge by their language preference and the region of residence. So let's find the probability that a randomly selected individual is a French speaker. So to find this probability, and assuming that each individual has an equally likely chance of being selected, we can take the total number of French speakers and divide this by the grand total. So from our table, we see that there are 69 individuals that prefer to speak French and a total of 248. So this probability is 69 divided by 248. Now note that this is the same as finding a marginal distribution. So now let's look at finding the probability that a randomly selected individual is a French speaker and is from the Atlantic. So to find this probability, we will look at the number of people which prefer to speak French and that is from the Atlantic, and we divide this by the grand total. And so the probability that they are a French speaker and they are from the Atlantic is going to be 9 out of 248. And note that this is the same as finding a joint distribution. So now, what is the probability that a randomly selected individual is from Quebec? And so we find this probability by taking the number of individuals that are from Quebec, and we divide this by the grand total. So this would be 55 out of 248. And again, this is another marginal distribution calculation. And lastly, what is the probability that a randomly selected individual prefers French, given that we have selected a Quebecer? And so for this probability, we are looking for a conditional probability. So we're given that they are from Quebec, and we are looking for the probability that they prefer to speak French. So mathematically, we write this as the probability that they speak French, given that they are from Quebec. And so to find this probability, we look at the total number of individuals from Quebec, which is 55, and we want to find the probability that they speak French. And so we take 50 and divide it by 55. And note that this is the same as finding a conditional distribution. Hence, this is called a conditional probability. So now let's look at some rules for finding the probabilities for the intersection of events. So the general multiplication rule says that we can find the probabilities of A and B by taking the probability of A and multiplying it by the probability of B given A. Alternatively, it could also be found by taking the probability of B and multiplying it by the probability of A given B. And so this formula can be obtained by rearranging the formula for the conditional probability. So let's take a look at an example. Consider a bag of marbles, 3 of which are blue and 4 of which are green. And suppose we select 2 marbles from the bag without replacement. So this means that once we remove the first marble, we don't place that marble back into the bag. So instead, we select another marble from the bag. So now, what is the probability that the first marble is blue and the second marble is green? So let's define the events here. So we'll let A be the event where the first marble is blue and B is the event where the second marble is green. So we're looking for the probability that the first marble is blue and the second marble is green. So this is the probability of A and B. So to find this probability, we use the general multiplication rule, which is the probability of A times the probability of B given A. So we're looking for the probability of A. So what is the probability that the first marble is a blue marble? Well, there are 3 blue marbles out of a total of 7 marbles in the bag, and so the probability that the first marble will be blue is going to be 3 out of 7. And now since we're selecting the marbles from the bag without replacement, this means that we're not returning the first blue marble from the bag. And so now there are only 6 marbles remaining in the bag when we go select our second marble. So now given that the first marble is blue, then what's the probability that the second marble will be green? Well, there are 4 green marbles remaining in the bag with 6 total in the bag. And so the probability of B given A is going to be 4 out of 6. And so now we can multiply these probabilities. We end up with 12 over 42. And this can be reduced to 2 out of 7. So we can now use conditional probabilities to define independent events. So we say that the events A and B are independent if and only if the probability of B is the same when we are given that A has occurred. So mathematically, this says that the conditional probability of B given A is equal to the probability of B. So in other words, the occurrence of A does not affect the probability of B. So knowing that A has already occurred, then if the conditional probability of B given A is the same as the probability of B, then this means that the events A and B are independent. And if we're given that A and B are independent events, then the multiplication rule for independent events can be simplified to the following equation. So we can calculate the probability of A and B by taking the probability of A and multiplying it by the probability of B. So as an example, let's consider the same bag of marbles where there are 3 blue and 4 green marbles. But now let's select the marbles from the bag with replacement, meaning that after we select the first marble, we will return this back into the bag and then select our second marble. So now what is the probability that the second marble is green? So if we define the events A and B as before, where the first marble is going to be blue as A, and the second marble is green, is the event B. So here we're looking for the probability of B. So there are 2 possibilities that can occur. Either that the first marble is a blue marble and then the second marble is green, or the first marble is green and the second marble is green. So now let's look for the probability that the first marble is blue and the second marble is green. So there are 3 blue marbles out of 7. So the probability that the first marble is blue is 3 out of 7. And since we're selecting the marbles with replacement, then there's going to be 3 blue marbles and 4 green marbles in the bag for the second marble. And so the probability that the second marble will be green is going to be 4 out of 7. Now we add this to the probability that the first marble is green times the second marble being green. So the probability that the first marble is green is going to be 4 out of 7. And the probability that the second marble is going to be green will also be 4 out of 7, since we are selecting the marbles with replacement. So these are the 2 possibilities for the second marble being green. So now we can add these together, and this gives us 12 over 49 plus 16 over 49. That gives us 28 over 49, which can be reduced to 4 out of 7. So now what is the probability that the second marble is green, given that the first marble is blue? So here we're looking for the conditional probability. So we want the probability that the second marble will be green, which is the event B, given that the first marble is blue. So we're given that A has occurred. So to find this probability, we can use the formula for the probability of B given A, which was the probability of A and B divided by the probability of A. So here we're looking for the probability that the first marble is blue and the second marble is green. So the probability of A and B is going to be 3 out of 7 times 4 out of 7. Okay, so that's the probability of A and B. So the probability of the first marble being blue and the second marble being green. And now we divide it by the probability of A. So the probability that the first marble is blue is going to be 3 out of 7. So now you can simplify this fraction. So you can notice that there is a common factor of 3 out of 7. So we can reduce this to 4 out of 7. So notice that from part B and from part A, both of these probabilities are 4 out of 7. So the conditional probability of B given A is the same as the probability of B. And so this tells us that the events A and B are independent events. So when we are selecting the marbles with replacement, then these events are independent. So now let's look at an example using contingency tables. So this table shows whether university students like coffee and or tea. So what is the probability that a randomly selected student likes tea? So to find the probability that a student likes tea, we look at the total number of students, which is 185 that like tea, and we divide this by the grand total. So that gives us 185 over 300. And here I'm going to look at the decimal value as well, and this will be useful for us in the later parts. So to 3 decimals, this would be approximately 0.617. And now let's find the probability that a randomly selected student likes tea, given that the student likes coffee. So here we are looking for a conditional probability. So we're looking for the probability that a student likes tea, given that they like coffee. So to find this probability, we look at just the number of students that like coffee, which is 245, and we want to find the number of students which also like tea. So this will be 165, and we divide this by 245. And as a decimal, this will be approximately 0.673. And now part C asks, does liking coffee and liking tea appear to be independent? So to answer this question, we're going to look at the probabilities that we calculated in parts A and part B. If these probabilities are equal, then this tells us that liking coffee and liking tea will be independent. So now let's compare our probabilities. We're given that the probability that a student likes tea, given that they like coffee, was 0.673. And in part A, we found that the probability that a student likes tea is 0.617. So notice that these probabilities are not equal. And because the conditional probability of liking tea, given that they like coffee, is not the same as the probability that the student likes tea, then this tells us that these events are not independent. And so what we observe is that given that a student already likes coffee, then there's a higher probability that the student will like tea as well. And so this tells us that these events are not independent. So this will conclude our lesson for this video, and we will finish the section in the next video where we will talk about the law of total probability. And I'll see you then.